A huge thank you to War Thunder for sponsoring this episode. This is your fifth sortie of the day. You stopped counting the hours after the third one. There was no briefing this time. Somebody handed you a coffee on the apron and pointed at a map. Ahead of you, the second wave is unloading. Tanks, troops and fuel. If they finish, you don't get to come back tomorrow. The first wave has already landed. You drank half your coffee before the canopy closed. You're so tired, everything aches, even your eyes won't focus on the radar properly. You blink hard, twice and force them back to the scope. The sun sits low behind you, throwing shadows out across the water ahead as you race the wave tops at 50 meters at over 1000 kilometers per hour. The moon is up over the fjord. You feel like it's watching you. The anti-ship missiles are gone, all of them, used up before midday. Now you fly with 4 rocket pods that weren't supposed to be necessary. You took off at first light with the rest of your wing, 8 aircraft. You came back over the coast by yourself. Now you're alone with Viggen, the 2 of you, the last of you. You try not to think about this morning, you worry about the wings instead. They fixed the wings, didn't they? You believe them, you have to. The next high G turn might be your last. You repeat the engine procedure. Don't slam that throttle at high alpha. Don't slam the throttle at high alpha. You've been saying it to yourself since the first sortie. The thing surges if you breathe on it wrong, and you're about to ask it for everything it has. Again. You stay with the systems, so you don't have to think about the others. Somewhere out there, NATO is supposed to be on the way. Someone said so this morning, but this morning feels like another country. The Soviets are already in the fjord. That sentence still doesn't sit right in your head. They crossed the Baltic and got through the coastal defences. They paid for every mile of it, and you paid them back. But it wasn't enough. They got through before noon. Now they're unloading in the same waters where your grandfather taught you to fish. You hear a voice in your head, one word, no. Fatigue be damned. You open the throttle, nose down. The water comes up, 40 meters, 30, 20, 10. The walls close in on either side. The light flattens, the color drains. The world shrinks to a strip of water ahead and the dark shape sitting on it. 3 ships, maybe 4, hard to tell. They came here to take this fjord. You're going to make sure they don't leave it. They see you. Tracer arcs out across the water, white and red reaching for you. You're flying as low as you dare. But above you, somewhere in the dusk, are the fighters that escorted them in. You can't see them, and you hope they can't see you. 3 seconds of straight and level. 3 seconds for the gunners on the decks to track you. You pickle the rockets. For a moment, time stands still. Then you brake hard left as you flash past the fleet back down to the water. You're no hero. You're just the last man still flying. And welcome to Aviation Republic. My name is Joe. 6 weeks. That was the gap between the first flight and the government committing billions of krona of Swedish taxpayers' money to the program. On the 8th of February 1967, prototype 37-1 left the runway at Malmslätt for the first time. Then, on the 20th of March, the government signed the order for 100 aircraft spread across the attack, reconnaissance and trainer variants. Early production orders weren't unusual in military aviation. What mattered was how much of the aircraft you were still discovering after you'd committed to building it and the margin of risk you were willing to carry into production. Maiden flights had proven basic handling, nothing more. The RM-8A engine was still in early evaluation, radar and weapons systems weren't fully operational, and the thrust reverser that made short field landings possible hadn't been proved beyond a handful of runs. From the moment the order was signed, the production line was running whether the design was ready or not. Testing would have to keep up, and it wouldn't be long before it was discovered how thin that margin of risk they signed up for really was. In Viggen's case, that margin was thin, and those risks weren't theoretical. But the first signs of that wasn't structural failure, it was human exposure to a system still being refined. Leonard Friel was in the cockpit of 37-1 on the morning of the 31st of May 1968 at Malmsland Airfield. This was the program's first prototype, the one that had made the type's maiden flight 15 months earlier. That morning, 37-1 was stationary on the runway when the ejection seat fired. The rocket motor launched Friel over 200 feet into the air. The Mark II seat had two firing handles, one above the headrest, one between the pilot's legs, and designed for zero altitude ejections, meaning it could save you at ground level, but only if the aircraft was moving at a minimum of 47 miles per hour. Below that speed, the parachute wouldn't have enough airflow to develop properly. Since the seat had fired while 37-1 had been stationary, the parachute never had a chance to open. Friel didn't survive. The aircraft, now pilotless, began rolling under its own residual thrust, veering off the concrete, crossing a drainage ditch and slamming into a hangar. An airframe carrying 700 sensors, the one that had logged one of the most important first flights in Swedish aviation history, was wrecked. The investigation never determined the precise cause. There is a theory that Friel dropped a checklist and snagged the lower firing handle as he reached down to retrieve it. But whether that's what happened or whether his movements displaced something else entirely, nobody saw. 37-1 would spend 3 years in the repair shop, and its test workload had to be absorbed by the remaining prototypes. A month later, Sweden's press began reporting that unit costs had doubled to 20 million krona. For the politicians who never wanted Viggen in the first place, any losses were writing the cancellation speech for them. Before we continue, that scenario at the start of this video, which I had a huge amount of fun making, you can fly yourself in War Thunder, the most comprehensive vehicle combat game ever made. It's free on PC, PlayStation, Xbox and mobile. You can take command of over 2,500 tanks, aircraft, helicopters and ships across 10 major nations, from 1920s biplanes and armoured cars through to modern fighter jets and main battle tanks. What sets it apart is how the machines are modelled. This isn't a health bar system. Every engine, fuel tank, weapon and crew member is simulated individually. When you take a hit, the X-ray view shows exactly where the round went, what it damaged and why the vehicle stopped working. There are 3 game modes to choose from depending on how far you want to take it. Arcade is fast and accessible. Simulator mode gives you the full cockpit experience with no shortcuts, and realistic gameplay sits in the middle. And you don't need specialist hardware, mouse and keyboard or a controller is enough, even in sim. I've been flying both the AJ37 and the JA37 Viggen. The AJS is all about low level strikes, treetop runs, getting in and out fast. The JA is a completely different aircraft, built for interception and dogfighting. Switching between the two really shows how different those roles are, and both of them are a real handful, well, in the best possible way. War Thunder has over 95 million players, and if you're into military aviation or Cold War systems, there's a lot here to get into. You can play for free right now using my links in the pinned comment or video description. For a limited period, new and returning players on PC and consoles who haven't played in the last 6 months will get a bonus pack including the premium vehicles, the exclusive Eagle of Valor, 100,000 Silver Lions and 7 days of premium access. So thanks again to War Thunder for sponsoring this video and making it possible for me to devote the 100 or so hours it takes to research, write and edit every episode. Goes a long way to keeping the tea flowing and the wife at bay. So now, on to the story. On the 7th of May 1969, Milton Moberg was in prototype 37-4 at Linköping for a series of high-speed ground runs to test the thrust reverser, the system that would make short-field operations in dispersed forest bases possible. Without it, you couldn't stop Viggen in 1,640 feet, and without 1,640-foot landings, Viggen was just another supersonic, albeit handsome aircraft that needed a proper runway. During a high-speed taxi run, Moberg initiated the reversing system. This involved closing the 3 large reverser doors in the ejector nozzle to deflect the engine exhaust forward. The moment the reverser doors closed and the exhaust blasted forward, the nose snapped sideways. He fought it, but the aircraft was already going where it wanted to go. It veered off the runway, overturned and caught fire. Moberg escaped the burning wreckage uninjured. The investigation into the crash found that the reversing thrust was being redirected in a way that interfered with the aerodynamic stability of the fin and wing. The thrust was creating directional imbalance severe enough to snap the nose sideways beyond the pilot's ability to correct with the nose steering or rudder. The immediate engineering fix was to redesign the reverser outlets to concentrate the exhaust towards the middle, angling the jets away from the vertical fin and control surfaces. Engineers believed this fix had mitigated the aerodynamic risk enough to proceed with series production. What they hadn't yet solved was the steering system itself. 2 prototypes wrecked and 1 pilot dead, and neither loss had come from the edge of the flight envelope. Both had come from systems the aircraft would have to rely on every single sortie. Every crashed airframe was a gift to the people who wanted to cancel Viggen and buy American. The program was losing airframes, losing the budget argument, and losing time. But Saab's response was immediate and practical. Because the 37-4 was not a total loss, Saab immediately salvaged the front fuselage from the wrecked aircraft and used it to build a replacement prototype, 37-7, which flew 6 months later. However, the resources diverted to that effort delayed the first flight of the 2-seat SK-37 trainer by a full year. After Friyo's death, Saab developed the Mark III ejection seat, a true 0-0 system, safe at 0 altitude and 0 speed, and was retrofitted across the entire fleet. Though the fix came too late for the man who proved that it was needed, but it would save 3 more lives before the decade was out. By the time initial testing concluded, the program had burned through 2,300 prototype flight hours at 200,000 krona an hour. The directional stability problems that had destroyed 37-4 were documented, understood in broad terms, and not yet solved, and the production line was already running ahead of the fixes. October 1970, Linköping. The first AJ37 serial 37001 rolled out of Saab's assembly hall, 53 feet long, assembled from hundreds of thousands of individual parts. Not a prototype or a testbed, but a production aircraft, the thing that Swedish Parliament had been arguing about since 1964. But production aircraft implied a confidence the program hadn't quite earned. Saab's production manager described the relationship between development and production bluntly. Development regarded production as a necessary evil. The engineers wanted to construct in peace. The production line needed frozen specifications and documentation delivered on schedule. When flight testing turned up problems, and it always did, drawings had to be revised, assembly sequences interrupted, and aircraft already on the line modified with the fixes that hadn't existed when their construction began. One example of this was the air intake, for which the design alone would not be frozen until 1974, 7 years after the first flight, 7 years of production aircraft built to specifications that kept shifting. The first 3 prototypes, 37-1 through to 37-3, had been built with a clean straight spine. But as testing pushed further into the transonic region, they developed what engineers call the zero torque problem, tilting moments that occurred even at zero lift, specifically when the aircraft transitioned between subsonic and supersonic speeds. External weapons were disturbing the vortex flow over the airframe, making the aircraft hard to tune out as speed changed. The trim requirements to tune this out were catastrophically large. The solution was an enlarged dorsal spine, later called a reinforcer bump. The bump smoothed the airflow over the fuselage and brought the center of pressure back under control, reducing the trim changes needed to stabilize the aircraft through the speed range. It also served a second purpose by conforming the fuselage more closely to the area rule, lowering transonic drag. But it came after series production had already started and aircraft were already moving down the production line. It caused what one engineer diplomatically called discussions between development and production. The main airframes had to be reconstructed at heavy cost, their structures modified with drawings redone, and all the airframes already built brought up to the new standard. It worked, but it was another example of the same problem. The aircraft was being corrected after it had already been committed to production, and because the design was still moving, the aircraft coming off the line weren't all entirely identical. The test program was no longer validating a single design, it was trying to keep pace with a moving one. The reinforcer bump wasn't the only aerodynamic fix that arrived after production had started. The prototypes had flown with a clean leading edge on the main wing. It looked elegant, it also stopped working the moment you hung anything underneath it. In part 1 we covered how the canard acts as a vortex generator. At high angles of attack, the canard throws turbulent high-energy air back over the main wing, delaying the stall and letting the aircraft fly slower than a pure delta ever could. That interaction between canard and wing was central to the whole concept. But when Saab moved the main undercarriage from the fuselage to the wings, it pushed the heavy weapons pylons further outboard. And when large external loads went on those pylons, they disturbed the vortex flow that the canard was generating. The aircraft became longitudinally unstable, pulled back on a stick with a full weapons load, and the nose didn't always go where you pointed it. The solution was a notch, a sawtooth or dogtooth in the leading edge of each wing, cut inboard of the outer pylon stations. At high angles of attack, the notch would generate its own concentrated vortex. That vortex would travel back over the wing surface, energizing the boundary layer and preventing the airflow from separating exactly where the external stalls were causing the most interference. It reinforced the canard's vortex. The two systems worked together to lock the longitudinal stability back into place. The sawtooth also helped in the transonic region. Around Mach 0.9, delta wings can become temperamental in roll. The vortex the sawtooths generated kept the airflow attached more evenly across both wings, dampening out the asymmetric lift that made deltas twitchy at those speeds. Though the fix would add a small amount of drag compared to the clean prototype wing, it was a trade-off the engineers were willing to accept. Not that it was a difficult choice to make, since it was a choice between a stable weapons platform that handled predictably under load or an elegant airframe that couldn't be trusted with weapons it was designed to carry. And though the series aircraft got the sawtooth, the early prototypes flew without it as they weren't going to be carrying stores. Pilots would later describe feeling the aerodynamic interaction during low-speed flight. At high angles of attack during the steep no-flare approaches that Viggen needed, the vortex from the canard was so powerful that it physically drummed against the main wing. Pilot accounts mention they could feel it through the airframe, the aircraft working to keep itself stable at speeds where conventional deltas would have long since departed. But that stability came with a cost. Once the pilot pulled into a hard turn, the induced drag from that big delta wing bled energy fast, with one pilot describing it as dragging a barn door behind you. Viggen could get into a fight, he just couldn't afford to stay in one for long. On the 23rd of February 1971, test pilot Ingemar Rasmussen took 37001 up for its maiden flight. The aircraft handled differently from the prototypes. For one, it was heavier, coming in at 23,400 pounds against the 21,700 the initial calculations had predicted. That weight hadn't appeared from nowhere. It was the accumulated cost of every structural reinforcement, every system addition and every fix applied during the years of testing that the original estimates hadn't anticipated. 4 months later, on the 21st of June 1971, the Swedish Air Force took delivery of its first Viggen, 10 days ahead of schedule, a schedule set 6 years earlier, before the accidents, before the cost overruns and the order cuts. Not bad considering delivery dates in military aviation programs almost never move forward. But because of heavy institutional pressure to deliver 37001, the aircraft was rolled out with a known unresolved stability issue. Though it had been partially corrected aerodynamically, it still had the same nose wheel steering and reverser system that had destroyed prototype 37-4 2 years earlier. And it wouldn't be long before the program gave its critics exactly the kind of headline they'd been waiting for. On the 14th of September 1971, General Gabriel Gautier, Chief of the French Air Force and one of de Gaulle's closest wartime associates, was at Malmslat for a technical presentation and flying display. Gautier wasn't shopping. France's Mirage F1, still 2 years from entering operational service, was already competing directly with Viggen for export contracts. The two aircraft had developed largely in parallel and would face off throughout the 1970s in Switzerland and India, to name a few, and the deal of the century competition for NATO orders. He wanted to see what the Swedish rival looked like up close. Test pilot Lars Bandelin drew the demonstration assignment. He'd just returned from Edwards Air Force Base, where he'd been flying the latest American machines, and he knew what a good aircraft felt like. The only aircraft available for this display flight was 37001, the same machine the Air Force had just taken delivery of 12 weeks earlier, and because Saab was also filming a documentary about the production program, Saab would combine his demonstration with footage for the cameras. The first sortie went fine. The second was supposed to include a short landing demonstration and immediate full reversal the moment the nosewheel touched down. Bandelin started his roll, took off, went into a steep climbing turn, rolled and then set up for landing for a long straight final. He pre-selected the reverser, set up the approach at 15 degrees angle of attack and put the main gear down on the runway. The moment the nosewheel touched the ground, the reverser engaged automatically. Bandelin stood on the brakes and gave the RM-8A full throttle. For this, he was rewarded with a violent yaw to the left, which he immediately countered with a boot full of right rudder. The nose almost came back towards the runway centre line. Almost, but not quite. The yaw continued. He kept the throttle forward, remembering what happened to Moberg during a similar incident. Pulling the power hadn't helped. The aircraft rotated more than 90 degrees, still carrying forward momentum, sliding sideways. At roughly 2,000 feet down the runway, the right landing gear hit grass, tearing it off and tipping the aircraft so the right wing dug into the ground. Viggen spun violently to the right, came up on its edge and slammed down onto its belly as the left gear ripped away. Then, fire! Fuel spraying under the fuselage at high pressure caught immediately. Flames broke into the cockpit through the climate system while the engine was still spinning down, filling it with smoke and acrid fumes. Bandelin held his breath, bent forward to protect his face from the burning plexiglass and went through the exit procedure step by step. Central harness first, then leg restraints, G-suit, life jacket. He yanked the canopy handle and the hood rose, slower than normal, infinitely slow. He jumped out to the right, stumbled and turned around to face his burning aircraft. Bandelin later said his first thought wasn't relief, it was guilt. He knew whose aircraft it was. KG Viggen, the first AJ37 divisional manager, needed 37001 to get the operational program started and overcome program delays. Bandelin had just wrecked it. The formal accident commission convened the following morning, and the chairman's questioning turned adversarial quickly. Why hadn't Bandolin followed the official emergency exit procedure? The manual said he should have crawled over the canopy screen and slid down the nose. Bandolin had jumped out the side instead, because the cockpit was on fire. Sitting in the room as an observer was Bengt Johnson, one of the big names at the test centre. Edwards trained like Bandolin and widely regarded as one of the sharpest technical evaluators in Swedish military aviation. He would later rise to become director of FMV Test, the Swedish Defence Materiel Administration. He was not the sort of man who stayed quiet when he thought someone was being stupid. In a gruff voice that silenced the room, he said, "Bandolin is sitting right here. He is alive. Is that not enough to prove he acted properly?" The chairman grunted, and nobody pressed the point further. It was pointed out afterwards that 37001 had a razor-sharp antenna mounted on the upper section of the nose. If Bandolin had followed the manual and slid down the nose, it would likely have done him serious harm. The exit procedure was quietly rewritten as a result. The investigation team analysed the films, measuring the marks on the runway, and combed through the maintenance records. They found 4 factors that had contributed to the accident. First, the reverse airflow blowing up over the wing created aerodynamic lift. The films showed the front part of the right wheel bogie physically lifting off the runway. The lift transferred weight from the main wheels onto the nose, unweighting the brakes precisely when Bandolin needed them most. Second, a recently replaced right brake disc combined with a bumpy runway produced an asymmetric braking force amplifying the turn. Third, the nose wheel steering had no self-centering tendency and gave no feedback through the rudder pedals. It was naturally destabilizing. Any sideways drift would grow on its own unless the pilot caught it instantly and countered with exactly the right input. Fourth and fatal, the steering had a maximum authority of 8.6 degrees in high speed. The measured yaw from the track ruts was 9.3 degrees. Bandolin was physically unable to cancel a turn that exceeded his steering's mechanical limit. The investigation pointed to the nose wheel steering as the primary cause of the accident. The geometric fix applied after Milton Moberg's accident with 37-4 had angled the reverser jets away from the tail, but the same rigid steering that couldn't counter the yaw in the prototype had been installed in the first production aircraft. The problem again had been documented when the reversal testing began in 1969. It just simply hadn't made it through to serial number 37001. Bandolin was back in the air before the week was out, though his pride took longer to heal than his burns, and his colleagues gave him a new nickname, Brandolin, brand being Swedish for fire. Gautier, a veteran fighter pilot himself from the war, presented him with what Bandolin described as a frightfully grey medal, delivered in a green box lined with green velvet and silk. The spoken tribute was brief. "You are welcome to the French Air Force and you can do what you want." It also came with an invitation to fly the Mirage. Bandolin recounts that when Gautier sat in the cockpit of prototype 37-5, he didn't rise from the aircraft without asking about everything. His detailed question led many to believe that his interest went far beyond ceremonial duties and into technical evaluation of a rival system. After the 37001 crash, full thrust reversal was prohibited from the fleet for 2 years, while simulations and ground tests validated the new nose-wheel steering. Only after this redesign did Viggen's ground handling become problem-free, but the production line couldn't wait. F7 Wing received their first aircraft in June 1972, a 2-seat SK-37 trainer. The wing became the type conversion school, and all 17 production SK-37s were delivered there between June 1972 and December 1973 to support that role. Conversion to Viggen would be a steep learning curve for the men transitioning from Lansen, where its pilot manual had been a thin binder in A5 format. Viggen's flight instructions filled multiple full-spine A4 binders. The physical growth in documentation was thanks to the huge leap in technical complexity. Pilots described the transition as a culture shock. The standard conversion course lasted 5 months and included between 45 and 50 flying hours in the SK-37 trainer, supplemented by approximately 25 hours in the flight simulator. The CK-37 computer was doing things that no Swedish aircraft had done before. In Lansen, the navigator had plotted positions on paper while the aircraft bucked and shook through turbulence at low level. In Viggen, the computer did it automatically. The first flight of the navigation system came in a modified Lansen that served as the electronic testbed for Viggen's avionics. The test pilot lined up on the runway, locked the course with a button and flew to the first waypoint, a church on the Swedish coast. When he arrived, the CK-37's calculated position fell precisely within the cemetery walls. He called it an eye-opener. After landing, he reported the result to Bengt Sjöberg, the key system lead, who, in the words of the pilot, shone like the sun upon hearing it. But the process they'd used for that flight wasn't acceptable from a pilot's workload perspective, and the system would need considerable automation before it was ready for operational use. One pilot after conversion put the mental load more bluntly. As soon as I put on my flight helmet, my IQ goes down by 50%. But the systems created other problems. Because the cockpit gave pilots more information than any previous Swedish aircraft, they found themselves looking down at the radar display at low altitude. At 65 feet above the Baltic, that could kill you, and several early accidents were traced exactly to this habit. The low altitude warning system was a blinking red light mounted on the edge of the radar display. It worked as long as the radar was switched on. The warning was electronically interlocked with the radar search mode. When pilots switched the radar off to avoid broadcasting their position, which they did frequently to remain stealthy, the warning was automatically disconnected. At low level, the safety system was unavailable during precisely the moments it was needed most. 2 aircraft later collided with the ground during night maneuvers, and the investigation determined that the aircraft's computers had accurate altitude and dive angle data and could have warned the pilots, but the system was disconnected because the radar wasn't on. The RM-8A engine itself had problems the Swedes couldn't fix. The engine's aerodynamic stability margin, the gap between its normal operating line and the point where the compressor would stall, was marginal. The shared air intake that fed the engine distorted airflow, reducing its tolerance for disturbance. Quick throttle movements, high angles of attack, high altitude, any of these could push the compressor past its limits. During development, engineers tried adjusting blade geometry and air bleeds, but the fundamental mismatch between the civilian JT8D jet engine, from which the RM-8A was derived, and Viggen's military requirements couldn't be engineered away. The compressor stalls were a constant headache, and by the time the first production aircraft were delivered in 1971, the main problems like oil fires had been mitigated, but the stall sensitivity couldn't be solved for the RM-8A. It was, with some hesitation, accepted as an operational reality. Pilots simply had to learn to manage it through procedure. Never touch the throttle during high angle of attack maneuvers. The fix would just have to wait for the RM-8B engine. And because no 2 early Viggens were quite alike, pilots reported handling anomalies and electronic glitches in flight that ground crews couldn't replicate afterwards. The Swedes called it the UA gap, or utan and markin, without remark. At the start of the program, 30 to 40% of all pilot-reported faults resulted in a UA gap. Environmental factors like vibration, G-load and temperature triggered errors in flight that vanished once the aircraft was stationary. The Air Force eventually reduced the UA gap rate to between 5 and 10% by introducing better diagnostic tools and refining fault-finding procedures. The variation between airframes was real enough that the Air Force tracked each individual aircraft throughout its life with a digital monitoring system that recorded approximately 200 different parameters and 450 signals, performing trend analysis against that specific machine's history. Later refinements expanded monitoring to roughly 1600 variables to improve fleet efficiency. There wasn't one Viggen, there were many slightly different ones. Prototype 37-1, after surviving 3 years accidental ejection and years of repairs, returned to flight testing in late 1971 and accumulated 1,133 flights over 12 years, including 183 spins. Its final flight came on the 27th of June 1979. 37-1 retired to the Flygvapen Museum in Malmstad. By 1973, the program had found its rhythm. Aircraft were rolling off the line, pilots were learning the new machine, and Saab was starting to believe the worst was behind them. They thought they'd stabilize the systems. Well, that was until the wings started breaking off. If you're enjoying this story, please take a quick second to hit the like button. It's a small gesture that makes a huge difference in helping me reach more aviation fans. Now, let's get back to the story. On the morning of the 11th of April 1974, Sergeant Ulla Younes was flying AJ37 number 37011 at roughly 8,200 feet. Nothing about the sortie was unusual. Well, that was until the wing came off. Without a moment's hesitation, Younes reached for the ejection handle and pulled. The Mark II seat launched him clear of a disintegrating airframe, coming down unharmed. What was left of the aircraft scattered across the Swedish countryside. 12 hypotheses were documented and reported to the Chief of the Air Force over the following months. Because Younes had been carrying rockets during a tactical exercise, the leading theory was that an accidental explosion had torn away the wing. That made sense on paper. The wreckage didn't clearly contradict it. And because the Air Force had a habit of blaming the pilots whenever a technical mystery turned up, Younes himself was subjected to extensive psychological testing and technical examination. But the investigators didn't get what they were looking for from him, nor did they get it from the wreckage. And so Viggens kept flying. For the next 18 months, every pilot who strapped into an AJ37 and pulled 4G or more was flying an aircraft that could disintegrate around them without warning. On the 6th of October 1975, Lieutenant Goethe Petersen was flying 37014 on a live firing exercise over Lake Vernon at roughly 1,000 feet when the airframe came apart. Petersen didn't have to reach for anything. The ejection system triggered automatically and shot him out as the aircraft broke up around him. He was recovered from the water uninjured. 4 days later, Lieutenant Harold Gattel of F-15 Wing took off in AJ37 number 37005 as part of a pair of Viggens over the Bothnian Sea for a simulated anti-ship missile attack roughly 12 miles offshore. As he pulled into an evasive maneuver, the wing broke off. Same failure as the previous 2 Viggens and the same violent disintegration. Once again, the automatic ejection system shot him out of the machine as it came apart. He landed in the water, struggling with the parachute cords in the open sea until the F-15 rescue helicopter hauled him out 20 minutes later. His wingman had watched it all happen before him and radioed the base. Back at F-15 Air Wing, Wing Commander Colonel Rolf Clemenson, on hearing the call, didn't wait for a formal report, immediately getting on the radio and ordering all F-15 aircraft cancel all activities immediately, return and land. 3 aircraft had now broken apart in 18 months. The pattern was undeniable, though the cause was not. And just like that, Sweden's all-weather maritime strike capability was grounded overnight, along with their reconnaissance variants. Swedish television, radio and press began spreading rumours of what the possible causes could be, at one point even suggesting sabotage by leftist groups had to be considered. In some officers' mess, pilots and engineers speculated whether the AJ37 was a dead end and whether the JA37 variant would ever be built, and if the whole program was finished and that they may never fly the aircraft again. Pilot confidence had, in the words of some officers, fallen sharply. The formal Defense Accident Investigation Board appointed Flight Director and Air Force pilot Ture Svensson as the technical expert. Svensson was a hybrid professional in the Swedish aerospace system, having earned his engineering degree in 1958 and receiving his pilot's wings in 1959. This dual background as both a senior technical officer and an active combat pilot gave him a unique perspective on aircraft performance and pilot safety. But when Svensson reported to F-15 Air Wing, officers he'd known for years greeted him with nothing more than stern faces and formal introductions. Who could blame them? The original investigation into the initial AJ37 loss in 1974, run in close cooperation with Saab, had failed to find the cause. Naturally, the trust was gone. Svensson wasn't going to repeat that. When he discovered that the Swedish Defence Materiel Administration and Saab were planning a friendly meeting in Linköping to discuss a joint investigation, he went there personally to shut it down. The Defence Accident Investigation Board, he told them, didn't accept parallel investigations being conducted without its representation. It was a move that created a permanent rift with some of his superiors. His boss, Gunnar Lindqvist, was furious. It was said that the two men never spoke again. But the die was cast and the investigation's independence was established. Saab wouldn't be setting the terms this time. The wing crime crisis, as it became known, now threatened the entire Viggen program. What followed was one of the most extensive investigations in Swedish military history. Navy divers and Air Force rescue teams worked through the target area on Lake Vernon for weeks, navigating around unexploded munitions from years of practice runs, bringing up pieces of 37014 little by little. First the front fuselage, then the tail fin, followed by the wings, and finally the rear fuselage with the RM-8A still attached. All the recovered sections were transported to the airfield workshop at F7 Su-10S and laid out on the hangar floor. The CK37 computer from 37014, recovered from the lake, was carefully dried and sent to Saab for examination. In part 1 of this series on Viggen, we covered this elegant machine, including the hand-threaded peppercorn-sized rings that made up the ferrite core memory. And we mentioned one property that nobody had expected to matter. Ferrite core memory holds its data without power. The CK37 had special power-off circuits designed to initiate a memory stop sequence during a power failure. This made sure that the final state of the memory was preserved as the voltage dropped, meaning that when the electricity is cut, the ones and zeros stay frozen in place. That property was to matter a great deal. The engineer given the job of reading out the memory later recalled that he had to start by picking snails out of the memory housing. But the real problem wasn't the wildlife. Ferrite core memory is destructive read, meaning that sensing each bit would erase that data. So if the right back wires were damaged, he'd get exactly one attempt. Read it once and the data is gone forever. Fortunately, the engineers got what they needed: height, speed, orientation, attitude angles, and G-loading from the final seconds before the power died. The data showed the pilot had been in a turn, pulling roughly 4.5 to 5 G. Nothing abnormal, no prohibited maneuvers or system failures before the brake. That ruled out pilot error. And because there was no signature of an explosion or fire before the structural failure, it ruled out sabotage too. And that was the problem. Viggen was designed to handle those G-loads, and if the structure was failing at relatively low G-loading, something was wrong with the airframe itself, not with how the pilot was flying it. While engineers were recovering the computer's memory, the materials team was already examining every fracture surface in the wreckage. On the 29th of October 1975, 19 days after the grounding, they put the left wing spar under a scanning electron microscope. And they found fatigue cracks with characteristic striations that tell you that metal has been bending back and forth until it gives up. The cracks had started at a bolt hole on the lower rear flange, one of the attachment points where the wing met the fuselage. What they discovered was that the gap between the edge of the bolt hole and the edge of the flange was just 2.6 millimeters. But why does this matter? Well, when you drill a hole for a structural member, you create a stress concentration. Every load the structure carries gets funneled through the material around that hole. The further the hole sits from the edge of the flange, the more metal there is to spread the load. Standard practice required at least 1.5 times the bolt diameter between the hole and the edge. On an 8mm bolt, that meant 12mm from the centre, or about 8mm of material between the hole and the edge. They had just 2.6. 2 days later, on the 31st of October, Svensson called Saab's technical director Eric Bratt and told him they'd found the cause. He asked Bratt to send the wing spar from 37011, the first crash, the one that had been sitting in Linköping for 18 months, to the materials laboratory for comparison. Bratt called back that afternoon. The same fatigue cracks were present in 37011. The answer had been in Saab's possession since April 1974, and in that time 2 more pilots had been shot out of disintegrating machines while they sat there in the warehouse. Bratt told Svensson that the realization felt heavy on the company. On the 6th of November, Svensson stood in front of Saab's technical staff in Linköping and showed them the images. He pointed out the 2.6mm gap and then pointed out the 8mm standard. This technical negligence allowing a 2.6mm gap where standard practice demanded 8mm was considered by Svensson as swearing in church. Saab had violated something considered fundamentally unquestionable, a breach of engineering protocol, one that had been missed by the company for years. After the briefing, Viggen project manager Ole Esping walked up to him and asked him whether he wasn't a bit early with the conclusion of fatigue. The company wasn't ready to accept it, but Svensson's team had already conclusively established the presence of unequivocal fatigue cracks originating from the spar's bolt holes. The first 27 production aircraft had all been built with the 12mm flange, and because the production line had been adjusting the design as it went, those airframes weren't even identical. 4 different spar configurations across the batch. Not one Viggen, but a family of slightly different machines sharing the same fundamental weakness. All the aircraft had to go back for a complete rebuild, their 12mm flanges replaced with 41mm ones. The work took months in which Sweden's newest all-weather maritime strike capability sat on the ground. Svensson was even taking sleeping pills to get through the nights. I read in one account that he dreamt of metal and aircraft parts dancing around him while he tried to sleep. When the first reinforced aircraft was cleared in March 1976, F-15 Air Wing Commander Colonel Rolf Clemenson didn't just sign off on it. He turned to Svensson after the technical briefing and asked, "We believe in you and what you found, but do you believe in this? Monday, our first aircraft is ready for flight. You get the mission, a full aerobatic display." Svensson's answer, "Of course, I'll do it with the greatest joy." That Monday morning, he climbed into the cockpit and flew a full aerobatic routine for the gathered pilots of F-15, the same men who'd greeted him with stiff faces many months earlier. When he landed, there was applause. The pilots were suddenly eager to fly again. After the success of his briefing at F-15, the same presentation was given at other wings, with a similarly positive response, officially ending the crisis of confidence within the Air Force. The fix wasn't just thicker flanges. The Air Force installed crack detection equipment across the fleet and committed regular inspections of every spar. The reinforced 41mm flanges were so overbuilt that no cracks have ever been found in them since. But the philosophy had changed. As one official put it, we must learn to live with the cracks. However, the program had survived. The wings were fixed, but surviving the crisis wasn't the same as being ready for what came next. The AJ37 had been built to do one job above all others, and that was to sink ships. By 1945, attacking warships from the air meant paying a heavy price. Anti-aircraft armament had increased 5-fold since 1942. Radar-guided guns could engage at ranges that would have seemed impossible 3 years earlier, and proximity fuses meant shells no longer had to hit an aircraft to bring it down. The close-range torpedo runs that had crippled the Italian fleet at Taranto were becoming increasingly costly, survivable only through mass coordinated attacks or luck. Survival meant striking from outside the fleet's defensive envelope. Sweden understood this problem better than most. The Baltic is relatively narrow, and Swedish planners expected the worst, a D-Day scale invasion, hundreds of Soviet ships carrying troops and armour, screened by surface escorts bristling with radar-guided guns and missiles. If that fleet ever sailed, the window to stop it would be measured in hours. Swedish planners needed a weapon that could find and kill ships at standoff range, launched by pilots who might never see their targets. They tried to build one from scratch. In 1957, the Air Force authorized Robot 330, a cruise missile designed to strike harbours and installations on the far side of the Baltic. The project pushed Swedish engineers into unfamiliar territory: compact navigation computers, transistorized electronics, and ferrite core memory. The work produced SANK, Sweden's first miniaturized digital computer and the direct ancestor of Viggen's CK-37. But Robot 330 itself never flew. In 1959, the government decided that manned aircraft, not missiles, would carry Sweden's strike capability. The cruise missile was cancelled, but the computer lived on. What Sweden did have was a tactical weapon that worked. The RB-04 had entered service with the A-32 Lansen in 1961, the world's first airborne autonomous anti-ship missile. Its gyro control system could be traced back to the German V-1 flying bomb, reverse engineered and refined by Swedish engineers who added an extra gyro for roll stabilization. Since the V-1 had a fatal weakness, RAF fighters learned to flip it with their wingtips, sending it tumbling to the ground. The Swedish version wouldn't make that mistake. By the time Viggen arrived, the weapon had evolved into the RB-04E, a sea-skimming missile with a frequency-hopping radar homing system, highly resistant to jamming and complete fire-and-forget autonomy. We'll cover the RB-04E in greater detail in Chapter 10. Lansen could carry the original RB-04, but it needed a two-man crew to make it work. The navigator handled radar, timing and position calculations while the pilot flew the aircraft, but only squadron leaders had the full navigation equipment and everyone else followed. The AJ37 changed that. The CK-37 computer replaced the human navigator, automating sighting, navigation and weapons release. Every aircraft had its own radar, its own computer and, crucially, the ability to find and strike a target without depending on anyone else in the formation. Each aircraft was an independent ship killer. But the AJ37 didn't find its own targets directly. It was one link in a chain that ended with the RB-04E, and that chain started long before the pilot strapped in. Sweden's coastline was ringed with radar stations, operated by the Navy and coastal defence forces watching the Baltic approaches. Ground controllers added what they could from the FRA, Sweden's Signals Intelligence Service, radio intercepts, radar emissions and anything else that hinted at where a Soviet convoy might be. The same feeds ran into Strill 60, the system that coordinated Swedish fighter defence. For attack pilots, Strill 60 was background noise. For the interceptor crews who'd one day fly the JA-37, it would be everything. But that's a story for part 3. But coastal radar stations couldn't see over the horizon, and intelligence reports couldn't tell you whether a contact was still where it had been an hour ago. For that, Sweden needed eyes in the air. From the outside, the SH-37 looked identical to its attack cousin. But where the AJ37 carried weapons to kill ships, the SH-37 carried the means to find them. It replaced the S-32C Lansen, the two-seat reconnaissance aircraft that needed a navigator to photograph the radar display or hand plot echoes onto a map. The pilot in the SH-37 had to do everything himself. To find ships, it was fitted with a maritime version of the AJ37 system, built by Ericsson and designated the PS-37-1/A. Everything about its design was focused towards one problem: finding ships in the Baltic against coastal clutter under jamming at low altitude. To work against Soviet jamming, the radar used two layers of defense. The first line was in the hands of the pilot, and the other had already been chosen before he left the ground. But let's start with what the AJ37 pilot had at his disposal. Radar works by broadcasting microwave pulses on a specific frequency and listening for the echoes. When the pulse hits something, a ship, a coastline, a rain cell, some of that energy reflects back, and the time it takes to return tells the radar how far away the target is and in which direction it lies. Which means the target's first line of defense was making sure that what the radar saw wasn't trustworthy or readable. Soviet warships carried jammers for exactly that reason. A jammer is simply a transmitter tuned to the same frequencies as the radar, but its job isn't to detect anything. Its job is to broadcast noise, fake echoes, or both, until the picture vanishes from the pilot's radar screen into a wash of false signals. If the pilot couldn't tell a ship from a jammer's fake, he couldn't launch his missile. Not because the missile wouldn't fly, but because he'd have no way of knowing what it was going to hit. A simple way to understand how a jammer works is to imagine having a conversation with a friend in a crowded pub, except the pub is full of convincing impersonators. You ask your friend a question, your friend answers, and at the same moment every impersonator answers in your friend's voice. You hear 100 replies and you can't tell which one is real. The radar has the same problem. It sends out a pulse, waits for the echo, and what comes back might be a real ship, or it might be a fake generated by the jammer to look like one. What the pilot had to counter any jamming was a set of 8 filters he could select from via a rotary switch mounted on the radar console. Each filter was designed to wash out the noise to tune out fake echoes from the real ones. One position turned the receiver's sensitivity down across the board so that only the strongest returns came through. A genuine echo from a ship at close range would still make it. A weaker fake echo from a distant jammer would fall below the threshold and disappear. The cost was that weaker genuine returns disappeared with it and ships at longer range stopped showing up. Another position activated a tracker lock. Once the radar had found the ship, it started tracking it. The lock would refuse to follow any signal that jumped suddenly in position or range, the way a jammer's fake would. Another narrowed the receiver's bandwidth, rejecting signals outside a tight frequency window. A real echo has a specific shape, a pulse of a particular duration on a particular frequency. Some types of jammers try to drown the picture by broadcasting broadband noise across a wide spread of frequencies. Narrow the receiver enough and only signals matching the exact shape of a real radar pulse get through and everything else is rejected. The pilot cycled through the 8 positions by hand, one at a time, watching the display for a picture he could trust. Some filters killed the jamming but wiped out the genuine returns along with it, leaving him with a clean screen that showed him nothing. So he would try the next one and the next until he found a filter that worked or worked the best. The second defense had been set on the ground. The magnetron, the radar's transmitter tube, could be tuned across the band of roughly 8,600 to 9,500 MHz. Ground crews set the operating frequency during maintenance rather than during flight. That choice determined what any opposing jammer had to work against. Which raises an obvious question. Wouldn't a Soviet jammer just cover that band looking for the Swedish radar? To answer that, it helps to understand what kind of jamming actually existed in the 1970s. There were 3 main approaches. The first was spot jamming, which concentrated the full power of the jammer on a single frequency. It was the most effective form of noise jamming when it worked. But it worked best if the operator had set the jammer to the frequency the radar was actually using. Set it wrong and the jammer was broadcasting thunder. at a patch of empty sky, while the radar, operated a few hundred megahertz away, saw nothing but its own clean returns. The second was barrage jamming, which took the opposite approach. Instead of concentrating all that power on one frequency, it spread the same power across a wide band. Somewhere in that band was the frequency the enemy radar was actually using. The jamming would hit it, but weakly, because the jammer's total output was now divided across 100 MHz instead of being pointed at just one. A clean receiver with good filtering could often pick the real signal out of the noise. Then there was sweep jamming that tried to bridge the two. This method operated by transmitting full power at a single frequency at any given moment and moved rapidly back and forth across a band. In theory, the sweep jammer would hit every frequency in the band with full power somewhere in the sweep cycle. In practice, a radar pulse that happened to fire while the sweep was at the other end of the band got through largely unaffected. All three techniques required pre-selection of either a frequency or a band, and the technology of the time couldn't adapt quickly enough to an unknown radar signature in real time. The Soviet Krivat-class frigate carried two systems that NATO called Bell Shroud and Bell Squat. Bell Shroud was the listener. When a hostile radar painted the ship, Bell Shroud detected the emission, estimated its frequency band, and reported the bearing of the source. It was a warning system, not a weapon. It told the ship's crew that it was being looked at and from which direction, but not much more. Bell Squat was the jammer itself. It was configured before deployment based on what signals intelligence said the enemy radars would be operating on. Even though the two systems worked side by side, Bell Squat lacked the automation to look up the measured frequency detected by Bell Shroud and retune in real time. Bell Squat transmitted on the pre-selected frequency settings, and if that frequency matched the radars, the jamming worked. If it didn't, the jammer was loud and largely ineffective. The theoretical alternative was a jammer that could detect a radar signal, identify its pulse shape and frequency, then retune to match, all inside the few seconds before the radar found its target. These kind of systems would become standard in the 1990s with automated signal processing, but in the 1970s the Krivat class simply didn't have the systems to do that quickly enough. So the magnetron's fixed frequency wasn't what defeated real-time jamming. The limitation was the lack of fast, automated retuning between detection and response. Weapons obviously don't appear overnight. A Soviet jammer purpose-built to defeat a specific Swedish radar or a missile seeker designed to home in on one takes years to develop. And the engineers building those weapons don't work from guesses. They work from data, detailed technical libraries built by signals intelligence units who'd spent peacetime years listening to Swedish radars and cataloguing every emission. Everything the radar did that could be detected at operational range was logged and filed. A generic jammer that scans a broad band is weak by design because it spreads its power across too many frequencies to overwhelm any specific radar effectively. And filters, good filters, reject most of what it generates anyway. But a jammer tuned exactly to the signature of a specific radar, such as the same frequency, the same pulse shape, the same timing, can generate convincing false targets in the radar display using a fraction of the power. A well-designed jammer lives or dies by the quality of that catalogue. Sweden's move was to make that catalogue perishable. The PS37-1/A tuned to one frequency this year would be tuned to a different one the next, chosen from anywhere in that 900 MHz band. The library the Soviets were building kept going out of date. Two defenses, two timescales. One was fought in a cockpit at the speed of the pilot's hands on that rotary switch, and the other was decided in the maintenance hangar. All of it was in service of the picture the pilot actually saw on his display. The PS-37-1A radar screen had 3 main modes, and the pilot moved between them depending on what he needed to do. The first was a radar map that handled navigation and long-range search. It painted the sea and coastline in a forward arc out to about 120 kilometers, with ships appearing as bright blips against the dark of the open sea. The display itself was wedge-shaped, narrow at the bottom where the aircraft's own position sat, widening toward the top where the far edge of the radar's reach extended. A contact appearing 120 kilometers out showed near the top of the screen, with plenty of room around it, but as the aircraft closed and a contact moved down the display towards the pilot's position, it crowded into a narrower and narrower band of space. By the time a ship was 30 kilometers away, it was sharing the lower third of the screen with every other contact the radar had in the same arc. The picture that had been easy to read at long range became a jumble at close range. Before the pilot could use the map mode at all, he had to tell the radar which environment he was flying over, and he did that with a switch on the radar panel marked with land and lake, the Swedish for lake being more or less the same for sea. I tried to pronounce the Swedish for lake. I failed miserably. So when he was going from feet dry to feet wet, he'd flick the switch. And these two settings existed because the radar picture those two environments produced looked nothing alike. Over open water, the sea surface returns a fairly uniform wash of weak signals, every wave reflecting the same weak signal in the same way, which meant a large, hard-edged ship stood out against the background like a headlight on a dark road. Over land, the picture was a mess. Every tree, building, rock face, shoreline, hill, and every inland lake sent back its own distinct return, and the radar display was filled with bright noise. What the land-lake switch actually changed was how the receiver processed all those signals. In lake mode, it was tuned to pull hard targets out of a smooth background. In land mode, it was tuned to handle the cluttered one. A pilot flying out from his forest base towards the Baltic would cross the coast and flick the switch to lake, and his display would clean itself up for the work ahead. On the way home, he'd do the opposite. The second mode was the B-scope. This mode stripped away the map and showed the same contacts the radar was detecting, but presented differently. Target bearing running across the screen, distance running up it, across a square display instead of a wedge. The practical difference was that contacts no longer bunched up towards the bottom of the screen as they got closer. On the B-scope, they stayed evenly spread, which meant two ships 10 kilometers apart looked 10 kilometers apart on the display, whether they were close to the aircraft or far away. The pilot would switch to the B-scope when he had contacts at close range and needed to see them clearly, or when he wanted a tighter, higher resolution picture of the corridor directly ahead of the aircraft. Third mode was where the radar kept him alive. In terrain avoidance mode, the radar was locked to 0 degrees elevation and painted only those returns sitting at the aircraft's own altitude. Everything else disappeared from his display. If he was flying along a valley at night, the valley walls would show as sharp returns on either side of the B-scope, while the clear air drawn down the middle showed as a dark corridor. He would fly towards those dark patches, as anything that showed up brightly was something that would call time on his mission. This was the AJ's answer to blind flying for a mountainous terrain. The pilot's manual describes it plainly. A canyon would appear on the display as a corridor with sharp returns either side and clear space between. A link to the pilot's manual is in the description below if you want to go deeper on it, but fair warning, it's in Swedish. At night or in bad weather, the radar corridor was the only picture the pilot had, and it was enough. 3 views on the same screen, wide for finding, tight for identifying, and narrower still for terrain following at night. Without a doubt, the workload was brutal. He had to manage the radar in all modes while monitoring the CK-37 computer, handling the RM-8A engine, and flying at wave-top height often in darkness, sometimes in fog. All the while, two systems logged what the pilot was seeing. In Lansen, a navigator had handled 3 jobs at once. He told the pilot what the radar was seeing in real time, he built a record of the sortie for the intelligence team on the ground, and he logged where the aircraft was and what it was doing when each echo appeared. With the navigator now gone, the aircraft systems had to do all of his jobs. For the intelligence team on the ground, the RKA system replaced the navigator's camera. Whenever the radar was active, the RKA photographed a screen, building a continuous record of every echo return. But a picture of the radar returns was only half the job. An echo on film is useless without knowing where the aircraft was, what heading it was on, and how it was flying when the echo appeared. In Lansen, the navigator had written that down by hand. In the SH-37, a second camera called the DKA photographed the aircraft's position, course, speed and pitch. 2 reels came back from every sortie, but they only made sense when read together on the ground by the intelligence team. The film from the RKA camera told them what the pilot had seen, and the film from the DKA told them where he had been and how the aircraft was flying when he saw it. The SH-37 was equipped with a forward camera that was good enough to identify ships, but it could not resolve antenna arrays or specific armament at a distance. For that, pilots had to fly low passes directly alongside the target, close enough to count rivets and sometimes too close enough to be provocative. Incident readiness ran 24 hours a day, every day of the year, and regional commanders used it constantly for ship identification, activity monitoring, and anything else that moved in Swedish waters. But finding a ship was half the problem. Proving what it was needed a different aircraft. The SF-37 carried no radar at all, and you could tell at a glance what it was from its distinctive stepped nose profile. Where the SH-37's nose housed the radar, the SF-37s held 6 cameras for panoramic low-altitude shots and high-altitude oblique detail for standoff photography. It also held an infrared system to detect heat signatures, and for night work the aircraft carried the MSK, the Morka Spanins capsule, or Darkness Reconnaissance Capsule, inherited from Draken. The SF-37 could photograph a ship in total darkness without anyone aboard knowing they'd been seen. The program paid off in the early 1980s when photographs taken from an SF-37 proved that the Soviet Tu-22M backfire bombers still carried their air refueling probes, weeks after the SALT I treaty had required them to be removed. With refueling, it could reach the United States. Without the probes, the Soviets could argue it was a theater weapon, not a strategic one, and keep it outside SALT's numerical limits. The photographs killed that argument. A single-seat reconnaissance aircraft had caught a superpower in a lie. Both aircraft carried 2 systems that turned every sortie into a signals intelligence mission. Apparat 27 was the warning receiver. Its sensors sat in bullet-shaped variants on the outer wing leading edges and on the rear fuselage, listening for hostile radar emissions and alerting the pilot through cockpit lights and an audio tone in his headset. It told him he was being looked at and from where. Apparat 47 recorded what Apparat 27 heard. Every time a Soviet search or fire control radar painted a reconnaissance Viggen, the recording ran. On the ground, analysts extracted the carrier frequency, the pulse repetition rate, the antenna scan pattern, and the mode changes. One file at a time, sortie after sortie, they built a technical catalogue of every Soviet radar operating in the Baltic. Every reconnaissance sortie came back with 2 kinds of intelligence: what the cameras had seen and what the radars had heard. But neither variant could complete the job alone, so they often flew together, one to find the target and one to prove what it was. We'll cover Apparatus 27 in more detail in Chapter 10. But neither variant could complete the job alone, so they often flew together, one to find the target, one to prove what it was. The SH-37 would sweep the area at long range and pass approximate bearings and ranges to the SF-37 by radio. Then they'd split, the SH-37 holding back to keep the radar picture, while the SF-37 ran in for the photographs. The photo aircraft would make high-speed passes, often at wave-top height, side-facing cameras capturing ship profiles as it flew past. Ake Olofsson, who commanded the reconnaissance division of F-13, called himself and his pilots masters of the hill, and of the Cold War they owned the Baltic. Part of the reason was that both aircraft carried weapons the Soviets had to take seriously. The SF-37 flew with two sidewinders on fuselage rails, the first Swedish reconnaissance aircraft ever to carry air-to-air missiles, and the SH-37 carried the same sidewinders with the option of an RB-04 on the centerline pylon. For a Soviet pilot flying out to intercept an SH-37, the sidewinders on its rails changed how close he could afford to push. For a destroyer captain, watching one make a low pass alongside his column, the missile strapped to its belly meant the Swede making the pass could also sink one of his ships. These were armed aircraft being treated as an intelligence nuisance, and the Soviets knew perfectly well they were more than just that. When the Soviet Union ran large-scale landing exercises in the southern Baltic during the 1980s, Olofsson's pilots monitored the shipping as practice. Over years of sorties, they learned how the escorts screened, how landing aircraft spaced themselves, how a column would reform after a weather break, and how a Krivac captain's behaviour changed between the first day of an exercise and the third. The intelligence that came back on film amounted to a working knowledge of Soviet method built one sortie at a time. By the time AJ37 crews were drilling their saturation tactics against a plotted enemy formation, the geometry they drilled against had been photographed, filmed and catalogued by the SH and SF divisions year after year, sortie after sortie. That was the hill Olofsson meant. But being masters of the hill couldn't last forever. For a while, Viggen's low-level performance let the reconnaissance pilots sit beneath Soviet radar, outrunning anything Moscow could scramble on short notice. But the MiG-23 flogger ended that with its radar that could look down. The sea clutter that had hidden an SF-37 at wave-top height no longer hid anything, and although the sidewinders were still on the rails and the RB-04 was still on the pylon, the sanctuary the reconnaissance pilots had operated from was gone. Encounters with Warsaw Pact fighters became routine rather than exceptional, and while most of them stayed professional, some didn't. During one mission off Östergötland off the Swedish east coast, a pair of SH-37s from F-13 wing was shadowing a Soviet formation in a long column when two Soviet fighters came down to intercept. One of the Soviet pilots lost control at low altitude and flew into the water, breaking apart between a Swedish aircraft. The cause was never made public, though what the incident showed was plainer than the cause itself. Moscow was prepared to fly hard enough at a pair of Swedish reconnaissance aircraft to lose one of its own pilots doing it, and whatever the SH and SF were bringing home was worth the risk to stop. After the crash, Soviet interceptors operated under severe restrictions for a time, and Swedish reconnaissance worked the area unopposed, though the restrictions didn't hold forever and the flogger didn't go away. By then, the reconnaissance divisions had built a picture of how the Soviet Baltic fleet would behave if they ever did try to invade. And if they ever did, they would be met by not one Viggen, they'd be met by swarms of ship killers. 4 AJ37s, no lights, 20 meters above the Baltic in the dark, pushing towards a simulated Soviet naval formation at the lowest altitude the aircraft could safely maintain. Alf Ingerson Thor, the legendary pilot, flew this type of mission many times across nearly 2,000 hours in Viggen, and he called these long dark nights exercises in disciplined fear. I've included links to interviews with Ingerson Thor in the description. At that altitude, in those conditions, the pilot became part of the system and, like any system, it only held together as long as its assumptions about the sea and the enemy held with it. The center of that system was the CK-37. Radar returns, Doppler ground speed, air data, fuel state, preloaded waypoints, all of them fed into a computer that held the picture together as a running solution, recalculated on every sweep of the radar, while the pilot split his concentration across 3 displays that vied for his attention. There was the head-up display, the radar screen, and a fuel gauge with 2 needles. One of them was an ordinary pointer, and it showed the fuel actually in the tanks as a percentage. But the other needle was shorter and striped like a barber's pole, and it didn't show fuel at all. It showed how much the CK-37 calculated he'd need to fly the rest of the route as planned and reach his primary landing site, and still have enough in reserve for one approach and landing. The pilots called it the tie or remen, and the gap between the 2 needles was his margin. When they met, he was flying on reserve. And that engine was a thirsty beast. At ground idle, the RM-8A sipped 1/3 of a litre a second. Pushed to military power, that went up to about 1.5 litres. At full afterburner, at low altitude, the engine drank 10 litres a second. Pushed harder, supersonic at sea level, with ram air boosting the fuel system to its hardware limit, that figure climbed to nearly 19 litres per second. But at 10 litres a second, the internal tanks would be empty in 9 minutes. At 19 litres a second, they'd be bone dry in under 5. The autopilot was juggling multiple tasks, dampening oscillations, holding attitude, trimming out the aircraft, but for the strike pilot it only had one job that mattered, stopping Viggen from killing him while he looked down at the radar. Over water it held 20 meters, over land it lifted to 30, 10 extra meters of margin for terrain the engineers weren't willing to underwrite. Still, low enough to clip a pine tree or 2. Holding 20 meters over moving water took 2 different altitude readings from 2 different systems and averaged against each other. The first system was a radar altimeter in the canard that read the distance to whatever was directly below, which at wavetop height was a sea surface that rose and fell with every wave. The second was the air data system, which cross-checked using pressure altitude as a smooth reference that ignored the sea entirely. The autopilot averaged the 2, so even though the sea moved, the aircraft didn't mirror the motion of the ocean. The autopilot held altitude, but the pilot still had to continuously scan every instrument in front of him, and to help him, the aircraft had a specific warning that triggered when it thought he was about to take Viggen for a swim. If the radar altitude dropped below 150 meters, roughly 500 feet, and at the same time fell below half of what the computer thought the safe altitude should be, the reference poles in the HUD and the altitude warning lamp blinked until he climbed out, what the pilots called the bottom warning. It wasn't warning him that he was too low, it was warning him that he was suddenly much lower than the computer thought he was. Usually that meant the ground was coming up to meet him faster than was expected. The aircraft had other ways of letting the pilot know when something went wrong. A stick shaker buzzed the control column if the angle of attack exceeded safe limits, accompanied by a pulsating audio tone. There were other tones like the master caution that was a single tone and 2 flashing red lamps in the glare shield, triggered by anything the system considered critical, such as engine fire, computer failure, low fuel, hydraulic loss and such like. Despite the shakers, tones and lights, 16 Viggens were lost to the sea or ground collisions over the aircraft's service life, controlled flight into terrain as the reports called it, and all it took was a moment's fixation on the wrong instrument or disorientation in the dark, and the Baltic would do the rest. But the sea wasn't the only thing that could kill him. The AJ37 that rode on every reconnaissance Viggen rode on every strike Viggen too. When a hostile radar painted the aircraft, 1 of 6 lights around the radar screen lit up. Each light covered a 60-degree slice of the horizon that helped the pilot understand the bearing of the hostile radar. The lights were also accompanied by a tone he heard in his headset, and the tone told him everything. Every radar in the world puts out pulses at some fixed rate. This is known as its pulse repetition frequency, or PRF. This can be anywhere from a few hundred pulses a second for a long-range search radar to several thousand a second for a fire control radar trying to hold a moving target. That rate is as distinctive as a fingerprint, and AJ37 took the incoming signal and converted its PRF straight into an audible pitch. A low PRF search radar produced a slow, low-pitched tone in the pilot's headset, heard as a sweeping beam passed over the aircraft every second or two. A high PRF tracking radar, focused and pinging the aircraft, illuminating it continuously, produced a rapid, much higher pitched tone. The difference between being looked at and being locked on was the difference between a growl and a squeal, and a pilot who'd flown enough sorties could tell which Soviet system had found him by pitch alone. When a radar locked onto the aircraft, it triggered a specific warning the Swedes called the ambulance tone, an alternating note between 1 and 2 kHz, unmistakable once heard. When the pilot did hear it, he had seconds to do something about it, because the next thing that happened was usually the missile. What AJ37 couldn't tell him was whether that missile had actually left the rail. Because once a Soviet fire control radar locked him up, whether it was guiding a missile or laying a gun, the tone didn't change. The moment before the shot and the moment after sounded exactly the same. The lock tone was the last real warning he'd get, and from that point on, he was guessing. Even the lock warning wasn't complete, because AJ37 detection lobes lay in the horizontal plane, fixed to the wing and tail antenna. The diagrams in the pilot manual showed the coverage as a series of lobes around the aircraft with clear blind spots above and below. A hostile radar painting the aircraft from within that horizontal plane triggered the lights. A radar directly above Viggen or below did not. That meant a Soviet fighter circling above the strike altitude could sweep Viggen with its radar and leave no trace on the panel, which is why in the start of the video we had the pilot betting his life that the fighters above couldn't see him. He had no way to know whether they were looking. Worse, because the detection ring was rigidly fixed to the airframe, a pilot banking hard to evade a surface-to-air missile would watch his own warning lights wink out as the bank tilted the ring off the threat. The ambulance tone would go silent, but it wouldn't mean he'd broken lock. It would mean he'd rolled his blind spot onto the enemy's face, and the radar that had been tracking him a second earlier was still tracking him now. If the pilot did hear the lock and wanted to do something about it, Viggen had one tool: Capsule KA, an external jamming pod mounted on an inner wing pylon. This was an older version of the U-22 ECM pod. It was a repeater type jammer. Rather than broadcasting noise across the band, it waited until a hostile radar painted it, then retransmitted a modified version of the incoming pulse back towards the source. The Swedes called this deceptive jamming. The pulse the enemy radar got back was close enough to its own to be processed and wrong enough to corrupt the tracking solution it was in the process of calculating. At its weakest, it muddied the radar's picture. At its strongest, it could keep a lock from forming at all. Once armed and warmed up, it worked automatically. It also worked, by most accounts, only some of the time. Repeater jamming was a technique the Soviets understood well, and their radar operators were being trained to recognize and filter the characteristic signature of a repeater's return. The KA pod's real value was against older fire control radars operated by crews who hadn't kept up with countermeasures training, and even then it bought pilots seconds, not safety. Against a missile already off the rail, it could only hope to confuse the ship's jammer enough to break contact, and nobody was confident it could. Even if it had worked every time, the pilot would still have paid for it on the pylon it occupied. The inner stations were where the RB-04E was mounted, and carrying a KA pod meant leaving a missile behind. A Viggen with a full anti-ship loadout had no active jammer. A Viggen with a jammer went to war with half its offensive weight. The same applied to the Capsule KB, the countermeasures family chaff and flare pod, because the AJ37 had no internal dispensers. If the formation wanted a cloud of metal to confuse a missile's radar seeker, or a burning flare to pull the infrared seeker off the aircraft, it came out of a pod, and the pod displaced a weapon. In short, Viggen couldn't hang a KA jammer and a KB dispenser and still carry two RB-104Es. Sweden solved the countermeasure problem by redistributing it. A strike group would go in heavy, pylons loaded for killing ships, and a second decoy group flew alongside, carrying the pods to throw out the chaff and flares. The formation as a whole had to hope the division of labour held long enough to reach the missile release point. Everything up to this point existed to answer two questions. How do you find the ships, and when do you fire? One problem was that the strike formation would have to run in at wave top height with the radar off to avoid detection, as flying at 20 meters kept the aircraft inside every Soviet ship's radar shadow. But the geometry worked both ways. Because the PS-37A's antenna was tilted half a degree below the horizon, meant that its beam struck the sea within a few kilometers, so all the pilot got back was clutter. To see a convoy 30 kilometers out, a pilot would have to climb, turn his radar on for only a handful of sweeps, and hope that that would be enough to capture the ships he was looking for. If and when the radar painted the targets on the screen, he would select memory mode. This mode would hold the echoes on the display for 30 seconds, after which he would drop back down to 20 meters while turning in an opposite direction. This maneuver was expected to work as the enemy's detection cycle was assumed to lag, and 30 seconds was thought to be long enough for the pilot to pick his targets without the Soviet radar painting his aircraft. After which the pilot worked through what the radar had caught using a cursor that he moved by using the radar control handle located on the left side console. He'd slew the cursor across each echo in turn, picking targets for the CK-37 computer rather than typing in coordinates, and the computer translated what he had picked into a firing solution while the aircraft continued to fly below the enemy's electronic horizon. Once the CK-37 had a firing solution, the doctrine asked the pilot to do the one thing he'd spent the whole run-in avoiding. He had to come up. The RB-04E had a generous launch envelope on paper, anywhere from 50 to 425 meters above the sea. But the CK-37 didn't fire from anywhere in that envelope. It fired from one specific altitude, and the pilot's manual, the SFI, called it the commanded altitude, fixed at 300 meters. Below 175 meters or above 425, the altitude warning lamp came on and stayed on, the system telling the pilot he was outside the firing solution window. The climb began at the pull-up distance, 40 kilometers out from the target. The pilot brought the nose up from 20 meters and climbed for 16 kilometers, leveling at 300 meters. By the time he reached the maximum release distance, 24 kilometers from the convoy, he was where the CK-37 wanted him, high enough for the missile's launch geometry to work, low enough that he hadn't given the convoy any longer to react than a doctrine could afford. The release window was the most exposed seconds of the mission. He was up where the convoy's radar could see him, flying straight and level so the CK-37 could close out its solution with no ability to maneuver until the stall's release light confirmed the missiles were off the rail. Then the pilot rolled into the swing dive, hard turned away from the convoy and back down to the wave tops, and the convoy got back just a brief tracking opportunity and nothing else. The RB-04E had been Viggen's primary anti-ship missile since the AJ37 entered service, a sea-skimming weapon that flew the last stretch of its attack on its own. The CK-37 worked the firing solution from air pressure, temperature and launch speed anywhere between Mach 0.7 and 0.92, and the missile's practical maximum range stayed around 20 kilometers. The targeting itself was simple. The pilot pointed the nose of the aircraft at the convoy and chose between two modes: NCAL, single target, in which the seeker would lock onto the first ship it could find, or group mode, in which the seeker would treat the convoy as a formation and hunt according to the logic set on the missile itself before takeoff. Once the CK-37 had the firing solution, all the pilot had to do was pull the trigger and then nose back down to the wave tops. No time to be holding course to admire one's handiwork and make the Soviet radar operator's job easier than it ought to be. Certainly not when the escorts could reach him with their radar-directed 30mm cannon or the newer SAN-4 missiles. Nor did they want to stick around to find out which fighters the Soviets had lurking above. After release, pilots scattered back to their dispersed bases while the RB-04E flew on without them, hugging the waves at 10 meters, low enough to delay detection until the final moments. As soon as the RB-04E was off the rail, it went to work. First, unlocking its control surfaces to pitch its nose down about 7 degrees as the missile fell away from the aircraft. A programmed yaw kicked it sideways from the rest of the salvo so the missiles wouldn't fly into each other on the way out. Only then did the seeker switch on, scanning the cone of sky ahead for something it could hit. When it did find something, it swept it 3 times before committing, and if the return vanished on the second pass, the seeker would throw it out as wave clutter or false echo and kept looking. Another failsafe was that if the closing speed was wrong, it assumed it had locked onto another missile flying in the same direction as itself and broke off. It also refused to lock onto anything it couldn't reach. A target too far off the missile's track for it to maneuver onto without losing energy got rejected on geometry alone before the validation had even started. In a cluttered environment, that caution could be the source of misses because returns flickered in and out for good reasons too, and the seeker couldn't tell a target on the edge of detection from a wave it had already dismissed. Training documentation called a successful lock an RB-04E seizure, which was a reasonable name for what it looked like. The seeker stopped searching, fixed on a return, and from that point on, the missile committed. When the convoy came into the seeker's cone, group mode looked for clusters of ships within about 8,900 feet of each other, roughly 1.5 nautical miles or 2,700 meters. Anything spaced wider than that and the seeker wouldn't consider it a group. This was a technical limit rather than a tactical preference set by how far the seeker could keep multiple returns inside the same sweep range, and it determined what kinds of formation the doctrine assumed it would be hunting. Naturally, the Soviet warships carried jammers designed to spoof or blank out incoming radar returns. If a ship's jammer broke the seeker's lock, the missile would actually home in on the jammer itself, tracking the signal source until either the jamming stopped or the range closed enough to reacquire on radar. So a ship that switched off its jammer could shake off the missile, but it would get the missile's attention via another method. A 200 kilogram shaped charge sat in the missile's nose, focused downwards rather than forwards, and it was designed this way to detonate above the target so the blast would go down through the deck as the missile flew over the ship. There were 3 proximity fuses that watched for the moment of fire. Electromagnetic, this one sensed the distortion the steel hull made in the Earth's magnetic field. Infrared, this one watched for the heat signatures of the engines and stacks against the cold sea, and the missile's own radar altimeter, ready to register the sudden altitude change as the beam crossed from open water onto a steel deck. A contact fuse was also installed in the nose as a separate backup if the missile actually struck the hull. Before the mission, the ground crew set the proximity logic with a switch on the missile's panel, the zone selector. In mode 1, the radar altimeter alone could trigger the warhead, simpler and faster. In mode 2, any two of the three fuses had to agree before the warhead fired, slower but harder to fool. Mode 2 was the setting used over rough sea, where the high waves could make a single sensor misread the geometry and detonate over water. Mode 1 was for a calm Baltic. The switches on the missile panel were labelled only with numbers because the seeker's electronics were classified, and the conscripted mechanics followed a checklist without being told exactly what the switches did. Until 4,000 meters out, the missile flew straight at the target. Inside that range, it began to lead, calculating where a ship would be rather than where it was. Then at 250 meters, the seeker shut off and the final quarter second was flown blind, trusting the fuses to do their work. If the missile somehow missed, the seeker came back on and locked onto the first thing it saw. Compare that to the RB-05A missile. When the pilot fired it, he had to steer it all the way to impact using a small joystick on the left side of the cockpit, tracking the missile by the flare burning on its tail, a point of light he had to keep lined up between his eye and the target until the thing hit. No camera feed or monitor, just the pilot, the flare and the joystick, while simultaneously flying at low level. The workload was so extreme it could only be used when the anti-aircraft threat was minor, and eventually its primary role shifted to work against large slow-moving targets where infrared missiles of the era couldn't achieve a lock. The RB-04E asked nothing of the pilot after release, and that was the difference that mattered. Imagine the damage one aircraft with two RB-04Es hitting their targets could cause. Now, what could 96 missiles do? 4 to 6 squadrons per wave, up to 48 aircraft, 2 missiles each. 96 RB-04Es arriving over the convoy inside a single coordinated salvo. That was the unit of attack the doctrine was built around. One missile finding a ship was a good start. 96 of them arriving within seconds of each other, and half of them finding any ship at all was the whole point. The only question was how many got through the defences. Well, that depended on three things working at once. First was the emission discipline. Only the lead broke radar silence, and only for the radar shock. The brief pop-up and handful of sweeps the doctrine had inherited from Lanson's era and refined for Viggen. The lead painted a convoy on his radar and then saved it in the memory mode. He then dropped back down to 20 meters and called the bearing and range to the formation by radio. The wingmen never turned on their radars. They flew the run-in on their own CK-37s and worked out the lead's call into a release point of their own. When they fired blind in the literal sense. They'd never seen a convoy on their own screens. What the convoy's electronic surveillance saw, if it saw anything, was a single brief pulse from a single aircraft somewhere out there beyond its own horizon. Soviet operators could probably classify the emission as a Viggen. The PS-37A signature was known, but the electronic picture gave them one threat, not dozens. And by the time they'd worked out what the pulse meant, the formation had already released and was turning for home. Alongside the strike group flew a decoy group, the Skeng group, which threw out flares and chaff to confuse infrared seekers and pull radar attention from the aircraft carrying the missiles. The second thing the saturation system depended on was that the missiles had been preset on the ground to spread themselves throughout the convoy. The same panel that carried the fuse mode switch carried three other settings the conscript mechanics worked through by checklist. The first switch was target row. This assigned each missile to the first, second or third row of the convoy as seen from the attacker, with the first row meaning the escort screen and the second and third rows meaning the interior, the troop carriers. The second one was the course offset. This biased the missiles heading by a few degrees left or right of the launch course. And finally there was angle jump. This told the missile to skip the first target it saw and lock on to the next one, so two adjacent missiles wouldn't fight over the same ship. The moment after launch, each missile steered away from the release heading by the course offset amount and held that bias for about 8 seconds before swinging back onto the attack track. Left pylon and right pylon missiles ignited their motors at different moments, the pylon position itself determining which fired first. A 2-second delay separated each pair from the same aircraft. By the time the salvo reached the convoy, the missiles were spread across bearing, altitude and time. And what the defending ship's radar saw was not a cluster but a succession of individual returns arriving from slightly different directions at slightly different heights and at slightly different times. The doctrine put the escorts first. The screening escorts carried the radar-directed guns and the SAN-4 batteries that made a strike costly, and if that anti-aircraft could be taken out of the picture, the follow-up waves could finish off the landing craft and troop carriers with rockets, bombs and cannon. The third thing the saturation system depended on was that every aircraft could find the release point on its own. Sweden's previous generation of strike aircraft, the A32 Lansen, had operated on the lead and follow model. Only the leader carried the navigation equipment and the trained navigator, so if the leader was lost or ground contact broke, the formation's joint capability went with him. The CK-37 ended that, so now every Viggen took off with the entire route already loaded. The system was accurate enough on dead reckoning alone to fly hundreds of miles and arrive within feet of a planned point. Ground control fed vectors via radio until the formation reached a point where it could break radar silence and scan for the convoy. But saturation only worked if every aircraft could reach its release point without help, and the spread on the missiles only mattered if each aircraft was where the spread expected it to be at the moment of release. For all the cleverness upstream, the missile itself was blind. The RB-04E carried no IFF transponder, so it had no way to tell friendly hulls from hostile ones once the seeker was on its way. It went where the seeker took it, and the seeker took it to the first ship that satisfied its rules. NATO observers later gave that kind of release a name, a Mad Dog Shot, a weapon launched into a target area to find whatever it could find, with no friend or foe filter and no controller in the loop. Sweden had handled the friend or foe problem upstream. The Air Force and Navy agreed on a line at sea before any strike went in. Inside the line, anything floating was a target. Outside of it, friendly. Probably. The missile didn't need to read the line because the planners had drawn it up for the missile. General Bert Stenfelder, who commanded Viggen squadrons and later wrote on the AJ37's combat doctrine, singled out the flank attack geometry as the one thing that consistently impressed foreign observers. He gave a high probability of damage with minimal exposure for the launching aircraft, and nobody else in Europe had built such a tactical doctrine. What those observers may not have fully grasped was how much of the saturation doctrine had been pre-built on the ground. Everything cleverer than a seeker was either upstream of it or running parallel to it. The pre-flight settings on the ground, the radio calls from the lead, the dead reckoning navigation, the line drawn at sea, all of it existed, so the seeker didn't have to be clever at all. The doctrine never assumed every RB-04E would arrive. Soviet shipborne defences such as the SAN-4 missiles, the AK-230 cannon and the jammers all existed to make sure they didn't, and the saturation maths had attrition built in from the beginning. What the doctrine couldn't assume was an unlimited supply. Enough missiles would find enough steel to break the formation apart, and that was all the doctrine asked of them. The point was never to sink every ship, it was to thin the screen badly enough that the survivors scattered and leave whatever was still afloat for the follow-up waves of rockets and bombs. Sweden produced 315 RB-04Es across the programme's lifetime. For a fleet of 106 AJ37s carrying 2 apiece, that was roughly 1.5 full-strength strikes before the stockpile ran dry, assuming nothing was held back for training, nothing failed on the rail, and every aircraft made it home to fly again. The stockpile was enough to work at full scale once, perhaps twice, and after that it stopped favouring the Defender. There was no reserve waiting in a bunker the planners hadn't counted, and Swedish industry wasn't going to produce a second batch in the hours an invasion would take to unfold. Once the stockpile was gone, the AJ37 stopped being the precision strike asset that Doctrine had built around it, and went back to being an aircraft with rocket pods and bombs and whatever else could be hung where the missiles used to be. The Doctrine was designed to work, it just wasn't designed to last. The RB-04Es had stripped the bark. That was the Swedish term for what the saturation doctrine was meant to achieve. Sink the escorts, peel the defensive screen off the convoy, and leave the troop carriers and landing craft underneath. Once the bark was off, the follow-up waves could finish the work with cheaper weapons. That meant rockets and bombs. The standard loadouts included 4 Bofors M70 rocket pods carrying 6 135mm rockets each, 24 rockets fired in a single volley lasting around half a second, or up to 16 120kg fragmentation bombs on special racks of 4 fitted with nose fuses and brake parachute. The AJ37 could also carry the RB-75 Maverick, a TV-guided weapon with a dedicated cockpit monitor, the EP-13 indicator mounted to the right of the HUD, that let the pilot lock onto a target before release and let the missile fly itself in. Attack profiles came at a price. A rocket run needed a pilot to climb to 300 meters for target acquisition, the same altitude the RB-04E launchers had used, only this time for rockets, not missiles. From there, the nose was high and the target sat somewhere below it, out of sight. The pilot would have to roll inverted to bring the target back into view through the top of the canopy, then pulled into a 6 or 7 degree dive and held a straight track for 3 to 5 seconds before firing. Now, a few seconds doesn't sound long until you're flying straight at radar-guided guns. Attacking a modern warship with rockets or the podded aiding cannon, which needed closing to less than 1,000 feet for effective fire, was what one test pilot called somewhat doubtful. Viggen came closest to being used in anger in October 1981, when a Soviet Whiskey-class submarine ran aground inside the Swedish archipelago, deep inside a restricted military zone, 6 miles from Karlskrona, Sweden's main naval base. It's not unheard of for subs to run aground, but they don't run aground there. And within hours a Soviet Krivet-class frigate along with a Kashin-class destroyer naval force was gathering just outside Sweden's territorial waters. And the obvious question was whether Moscow would attempt a forcible rescue. Viggen squadrons went to high alert, and Wing Commander at F-13 Norrköping chose a graduated response. If the Soviets did try a rescue, they would be sent a warning shot with 120kg bombs that would be dropped ahead of the Soviet warships, sending a shockwave through the hull that nobody on board would miss. And in the event they needed something to focus their attentions, Viggens would also carry the RB-04Es. Jan Andersson, flying an SF-37, made low-altitude passes to photograph the Krivet, and what he came back with stuck with him afterwards. Every door on the ship was closed and no personnel on deck, and Andersson later described the run as leaving him with an unpleasant feeling. The frigate wasn't waiting out a diplomatic incident, it was waiting for something more serious. Andersson took the pictures and got out, but the coverage didn't. Around-the-clock photo runs continued for 10 days, with Viggens visibly loaded with live ordnance the whole time. On the 10th day, the submarine was released and towed out. The Soviet task force followed it into international waters as the alert stood down. Moscow never attempted the rescue. The Swedes called the incident "whiskey on the rocks," but nobody was laughing. For 10 days, a neutral country had a Soviet task force at combat readiness on its doorstep. Viggen, that had been built to sink Soviet ships, was trying so very hard not to. There was a problem the RB-04E couldn't solve, and it had been there from the beginning. The PS-37A radar we covered in Chapter 9 was built for searching for surface contacts out on the Baltic and the coastline, and within that remit it did everything asked of it. But it wasn't a pulse Doppler radar though, which meant it had no way to separate moving contacts from the ground they were moving across. It saw shapes and shadows. A large convoy on flat, open ground might appear as a grainy smudge of bright returns that an experienced pilot could work with. A lone vehicle vanished into the noise. Their radar simply couldn't tell the difference between a tank and a rock, and it left that almost impossible task to the pilot's experience. Against aircraft, the problem was worse. A MiG or Su-24 flying fast and low to sit amongst the treetops was a single small contact moving across a background filled with ground returns, and without a motion filter there was no way to lift it out of that background. Soviet intelligence services had been mapping Swedish radar capabilities for years, and when they worked out what the PS-37A couldn't see, that knowledge was passed down to operational pilots as tactical guidance. The tactic was the mirror image of Viggen's own approach to Soviet ships. What worked for the defenders worked for the intruders. In practice, an AJ37's intercept followed a predictable and frustrating pattern. Ground control called the contact and fed head-ins. The pilot turned towards the threat, brought the radar to bear and saw nothing usable, only a wash of returns. The target might be there, buried somewhere in the clutter, but there was no way to isolate it. By the time an enemy aircraft broke out visually, if it ever did, the geometry was already lost, a close-range encounter the pilot hadn't planned for against an opponent who might already have a firing solution. Attack units pulled quick reaction duty as a stopgap, but only when conditions favoured visual interception. The AJ37 was restricted to daylight and clear weather. Without the data links fitted to later variants, pilots depended entirely on verbal ground control to find their targets. In practice, that meant summer months, when long days and good visibility made visual intercepts possible. The rest of the year, the job fell to the J-35 Draken, which could fly the missions in weather the AJ-37 couldn't. Everything that worked against Soviet ships failed against Soviet aircraft. The limitations didn't stop with radar blindness. Back in October 1962, the project specification had dropped the internal cannon. Doctrine at the time held that missiles would replace guns entirely within a decade, and the RM-8 engine was so much wider than its predecessors that the fuselage structure had to be made slimmer to meet area rule requirements, leaving no room for a gun in any case. The weight hunt to keep the aircraft weight down had forced sacrifices everywhere, and the cannon was one of them. On paper, it added up. In service, the pilots flying the aircraft called it a mistake, and the reason had less to do with dogfighting than with what happened after the missiles had been fired. Once the RB-04Es were expended, the AJ-37 shifted to unguided weapons mode for its second strike with rockets, bombs, and later the RB-75 Maverick. A built-in cannon would have given the pilot a cheap, always available fourth option for strafing follow-up targets, landing craft, vehicles, lightly armed escorts. Without one, the Air Force bodged the gap with external cannon pods, but the ballistics were poor and pilots had to close to roughly 300 meters to have any realistic chance of a hit. The same close-range knife-fighting distance the rocket runs needed against radar-guided anti-aircraft artillery that could engage from several thousand meters out. The lack of a gun also hurt in a dogfight, where the throttle restrictions made energy management difficult enough without being limited to missile armament. But the air-to-air case was the easier one to make, and it was the case the critics made the most loudly. The aircraft designation was the admission, AJ37, AJ standing for Attack Jack, Attack Fighter. The attack role came first in the name, and that was intentional. The J for Jack, the fighter role, was there in the designation, but it was never meant as a co-equal mission. The aircraft had been built to fly low, fly fast, and sink ships. Fighting other aircraft was what it would do if it had to, but not what it was built for. The AJ37 was effectively a ship killer that had been given some fighter capabilities along the way, not a fighter that had been given some strike capabilities. Then there was the engine. The RM-8A's throttle restrictions were manageable during attack profiles. In a dogfight where energy management meant survival, it was a liability the pilot couldn't afford. By the late 1960s, Draken was aging. Its radar couldn't look down either, but at least it carried guns and could be thrown around the sky without the pilot having to worry too much about engine surges. The budget for a fighter variant of Viggen had been approved in 1968, but the program spent 10 years fighting for its life. The JA-37 came within a single question mark of never being built. During the 1965 defense investigation, an Army memorandum argued that ground forces should be funded at the Air Force's expense, and the investigation chairman wrote 5 words in the margin of that report that no one in the Air Force forgot. It read, "No development and production of JA-37?" The question mark was all that stood between the fighter variant and cancellation. By 1985, the government had to modify 66 J-35 F-2 Draken airframes into the J-35J standard just to keep an interceptor force alive while waiting for the JA-37. The AJ-37 had done what the doctrine had asked of it. It could sink ships, survive the mission, and operate from forest roads with conscript ground crews. But it couldn't win a dogfight, and Sweden couldn't afford a strike fleet that couldn't defend itself. Viggen had been conceived as a unified aircraft, one airframe for attack, interception and reconnaissance. The Supreme Commander's specification of September 1961 had set the terms. One production line, one set of jigs, one supply chain. Sweden just couldn't afford 5 separate programs. For the first 3 variants, the logic held. On the SF-37, radar gave way to cameras. The SH-37 kept its radar for maritime reconnaissance. For training, Saab added a second seat. All of these machines shared the same wings, engine and structure. But the program had learnt something from the wing spar crisis, from the weight growth, from every fix that had been absorbed into a structure originally drawn in 1962. Not planned margin that existed because the engineers had overbuilt where they weren't sure, and because the production line had learned how to modify aircraft that were already flying. For attack, training and reconnaissance, the concept had worked. For interception, it didn't. The next step couldn't be an adaptation, it had to be reconstruction. Sweden had built a ship killer. Now it needed a fighter, and the fight to build it would take years. Before you go, a big thank you again to War Thunder for sponsoring today's episode. If Viggen's gotten under your skin after all that, and honestly, how could it not? You can fly her yourself in War Thunder. Play on PC, PlayStation, Xbox and mobile. Use the links in the pinned comment or the video description to sign up. New players and anyone coming back after 6 months away will get a massive bonus pack on PC and consoles multiple premium vehicles, the Eagle of Valor decoration, 100,000 silver lions, and 7 days of premium account time. It's available for a limited period only. So, thank you for watching. Until next time, toodaloo.